Lecture 1, Introduction to Microprocessors and Microcontrollers. We start with Introduction to the Microprocessor and Computer. Bit, what does bit mean? A bit is a binary digit that can have the value 0 or 1. Bit, binary digit. This is what's bit. Bit 0 binary digit 0 or 1. Byte is defined as 8 bits. So byte is a set of zeros and ones of 8 digits only. Nibble is half a byte or 4 bits only. Word is 2 bytes or 16 bits. Double word is a pair of words or 32 bits. Be careful about these two definitions because number of bytes or bits in word and double word differ from one microprocessor to another. It differs and depends on the type of the microprocessor or microcomputer. So not necessarily always this applies for such definition. Word 16 bits and 30 bits for Intel. We will see that for Intel microprocessors. Kilobyte. A kilobyte is 2 of power 10 bytes, which is 1024 bytes. So 2 of power 10, this is 1024. 2 of power 10 bytes, this is 124 bytes. Example. For example, 2 of power 10 bytes equals 124 bytes and equal to 1 kilobyte. 1 kilobyte. If we subtract this number 124 from 1, 124 minus 1, this gives us 124, 3 in decimal, which is in hexa is 3FF. This is important to understand. We will explain later why we subtracted this number, the 1 kilo from 1, to get this number or this one in hexa. Example 2. 2 of power 16. We can divide it into two numbers just to get 1 kilo here. So 2 of power 10, which is 1 kilo, and 2 of power 6. So we will write this as K, as kilo. And this one, 2 of power 6, is 64. So we have 64 kilobyte. 2 of power 16 in decimal is this number. If we subtract it from 1, we will get this one. In hexa is 4 times F, 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 F. Megabyte. Megabyte is 2 of power 20 bytes. This this number in decimal is this number 1,000,000 1,048,000 and 576 bytes, which equals 1 megabyte. So this is megabyte. 2 of power 20 is 1 megabyte. Minus 1, we will get this number in decimal and this number in hexa. You see, 1 kilobyte is 3FF. 64 kilobyte, this is 2 of power 10, this is 2 of power 16, 64 kilobyte is 4 Fs. 2 of power 16, 2 of power 20 is 1 megabyte. 2 of power 20, this is 5 Fs in hexa. Gigabyte, which is 2 of power 30, and in decimal is this big, very big number in bytes. If we write, for example, 2 of power 24, and we want to find it in terms of megabytes, that means 2 of power 20. So what we do, we will separate this number intentionally to have this one. Why? To write it in mega. So this is what we are doing now. 2 of power 24 is 2 of power 20 multiplied by 2 of power 4. And this one is 16. This one is mega. So we will have 16 megabyte. Megabyte. Programming advancements, machine language. Machine language was constructed of ones and zeros, the binary digits that we explained in the previous slide, using binary codes that were stored in the computer memory system as groups of instructions called programs. Assembly language. The assembly allows the programmer to use mnemonic codes such as add for addition in place of a binary number such as this one. So instead of writing our program in machine language using ones and zeros like this one, assembly allows us to replace these digits, these bits, into specific mnemonic codes such as add to simplify programming for programmers. This was in 1950s. Flowmatic. This is the first high-level programming language. Using this language, computers became easier to program. This was in 1957. Fortran, Algol, COBOL, RPG, BASIC, Pascal, and C and C++. All of these programs are high-level programming languages, and ADA as well. Now we will have a look at the early 8-bit microprocessors. The manufacturer is Fairchild. The part number is F8. For Intel, the part number is 8080. for most technology manufacturer is 6502, Motorola MC 6800, for National Semiconductor IMP8, Rockwell International PPS8, Zilog Z8. Of these early microprocessors, only Intel and Motorola continue successfully to create newer and improved versions of microprocessors. The microprocessor 8086, 8088, 8086 and one in the middle. So this version is an advanced version of this one. So it means it uses the same technology but with some advanced features. 81, 88 or 80, 88 and one in the middle, it means that this microprocessor uses this technology with a new advanced features. 80, 86 and 2 in the middle. The same thing, this is the same technology as this with advanced technology of this one. This is why we have here one in the middle and two here in the middle. The same thing applies for this type 8086 and 8086 for in the middle. And then this company that that produces these types of microprocessor, it's Intel company. So they stopped using numbers. They started using Pentium. This word, Pentium. Pentium Pro, advanced version of Pentium. Pentium 2, and Pentium 4 and Pentium 4. Pentium 3 and Pentium 4, and there are too many versions of Pentium 4, advanced versions of Pentium 4. The microprocessor comes another chip with it, which is memory system. The memory system, such as RAM, dynamic RAM, or DRAM, static RAM. So there are different memories here. We have dynamic here, static RAM, cache, read-only memory, ROM, read-only memory, ROM, flash memory, EEPROM, EEPROM, SDRAM, RAM BVS. So different types of memories. RAMs, we can write and read from RAMs. ROM, we can only read only memory, read from this memory. It means we can take data from this memory, but we cannot write inside this memory. With RAM, we can read, we can write, we can read. This is the difference between RAM and ROM. Microprocessor sends instructions to memory to ask to read or write, depends whether the instruction was for reading or for writing, and get information from the memory. Input-output system is another part of the microprocessor-based personal computer system. Input-output system, such as a printer, serial communications, floppy disk drive, which in our days disappeared, hard disk drive, mouse, CD-ROM drive, plotter, and keyboard, monitor, tape backup, scanner, DVD, etc. The microprocessor sends instruction to the input-output system and wait for an acknowledge to process the response from the input-output system. These arrows that we see here, they represent wires, and we call these wires buses. What's a bus? A bus is set of common connections that carry the same type of information. Now let's have a look at the simple architecture of the microprocessor. See what we have here. This is a microprocessor, or we call it CPU also. CPU, Central Processing Unit. And this part is ROM, this part is RAM, keyboard as an example of an input device, and this is a printer as an example of an output device. So these two devices are an input-output they are input-output devices. Now, the microprocessor will send instructions to RAM or ROM through a bus. This bus is called address. So this address, this address will go inside RAM or the ROM in a specific unique place, unique location. MRDC, this is memory. RD stands for read, C for control. So this pin will send logic 0 to ROM or RAM to tell them memory, ROM or RAM. I'm coming to read, so this pin, this signal, this bit that will be sent through this pin is just a control pin to tell these two chips, these two devices, that the microprocessor wants to read from this RAM or ROM to read something. So the microprocessor tells them about this, send them the address. If there is any another chips or another devices, we'll do the same thing with them. And the ROM or RAM, after getting this instruction or instructions to that specific address, will respond, will acknowledge that, and send the information, the data, through in this direction to the microprocessor. These are wires that will carry this data. You see, these wires also are buses. It's a bus. We call it a bus to carry what? The data. This is why we call this bus data bus. So we have two buses. We have this is one pin for control to tell them that that the microprocessor wants to reach something, sends the address with the with which location to it wants the microprocessor to take the data. So the ROM and RAM, the ROM or RAM will respond by sending this data through the data bus to the microprocessor in this direction. The RAM can also, as we said in the previous slide, that the RAM read-write memory chip can not only read as ROM does, but only can write. We can write on it. We can store data inside it. So we added this arrow to this chip. Not only this one. This one, it means it's already read from the memory, from RAM. Okay. But this one, it means can write inside the memory. Okay. This is the arrow that's missing here because it is wrong. We cannot write inside it. And the same thing, we have another pin only for the input-output devices, I/O input-output devices for read C control. So this control is to tell the keyboard that the microprocessor wants to read what this user is typing now, wants to read it, to take it, to pick it up to the processor to process it. Is the user now make calculations or hits some keys? Okay, so this pin will send a signal telling this keyboard, okay, I'm ready to receive the data that the user is typing now. Send address here, and it goes, of course, if there are other devices such as keyboard or any input device, and will take the data that the user already typed. Send this data to the microprocessor to process it. This is why we call it processor. Processor. Why micro? Because the chips and electronic elements inside this chip are very, very small. Processor because it processes arithmetic and logical operations. This is why we call it a processor. So it will take the information through the data bus, send it to the microprocessor to process it. And after processing it, it will store it in the memory. It will save it in the memory because we can write inside. Write, it means we can store inside the RAM, this RAM. After processing, the microprocessor can send again through the address bus to some location, to a location, specific location or locations to save the processed data. This pin is memory write control. So this pin is we will send special signal to write when this process needs to write, to store, to save inside the RAM. It will activate this chip through using this control pin. Will send a signal asking to open or to give a permission to write on it, and can go to another devices such as any device that has the ability to write on it. Printer, we have also special control pin to write. See, this is our D. This one R. Sorry, this one for input-output devices. So these both pins of the chip, or the microprocessor chip, are for input devices. One for read, the other one for write. For memory, we have also two pins for write and read. This one also will send a signal asking the printer or telling the printer that a printing process is coming up. So and can of course can send the same signal or other signals to such devices. I mean output devices. And the data bus, the microprocessor will send the data that needs to be printed using this printer. And others bus will be connected to other devices if they exist. The same thing for data bus. So the if we need to summarize the idea behind this simple structure, the microprocessor reads the contents of a memory location by sending the memory an address through the address bus. It sends the memory read control signal, this one MRDC, memory read control, to cause memory to read data, and the data read from memory are passed to the microprocessor through the data bus. Now let's have a look at the Intel family of microprocessor bus and memory sizes. For the microprocessor of Intel 8088, the data bus width is 8. The data bus width is 8. What does width for data bus? It means, well, what's 8? What does 8 mean? It means we are allowed to send data with size 8 bits only. So width or size 8 bits, it means 8 wires. 1, 2, 3, 4, 5, 6, 7, 8. 8 wires. Each of them carries either 1 or 0. Either 1 or 0. So we have a set of 8 bits for data bus for this Intel microprocessor 8088. The address bus size or width is 20. It means we have 20 wires, 1, 2, all the way to 20. So 20 bits will be carried by these 20 wires. Each of them will carry either 0 or 1. Memory size, the memory size is 1 mega. 1 mega, what's this, the memory size? We will explain this now. 20, the address bus, 20. If we raise this 20 to the base 2, because these are binary numbers, the result is this big decimal number, and this is the same number in hexadecimal form. The address, because we are talking about the address, we took this number from the address bus, ends at the address or memory location. So we have addresses of 20 bits. What does that mean? See, we will subtract this decimal number minus 1. We will subtract it from 1. The result is this number. And in hexa is this number. F, 5 Fs. After subtracting this number 2 of 20 of power 20 minus 1, we got this one. If you remember, I told you that we will see why we did this subtraction in the previous slides. Here we will explain why. See, this number in hexa, we wrote it here, and the first number is here with 1, 2, 3, 4, 5 digits. 5, remember, these digits are in hexa. These digits are in hexa. Okay, so the total number of bits, we have 5 hexadecimal numbers. It means 5 multiplied by 4, we will have 20 bits. So these are 20 bits. These are 20 bits. These 20 bits or these 5Fs came from this calculation, from this subtraction. And these are zeros. We wrote it here. Why? To explain that the address bus, when we say the width is 20, it means we have too many addresses there. Started with these zeros, ends at these Fs. This is why we subtracted minus 1. Why? Because we use 0 in the beginning. This is the beginning address. This is the beginning address, but the total from 5 zeros to 5 Fs is 2 of power 20, or in decimal this number, or in hexa this number. So we have to do this subtraction to get the last address here, and this is the beginning address, and here are the data. So 20, all of this is 2 of power 20. Data of this width will be here on the data bus, on the address bus, sorry. The data bus are here. I will explain this now. 1 megabyte, so all of this is 1 megabyte. These are 8 bits. See, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7, 8. 8 bits. These are the 8 bits. Will be stored in 1 byte. So this is why we say 1 megabyte. 1 megabyte. This is the first 1 byte. Here the second byte. So the total of these two addresses are 2 bytes. This is the third one. Now the total is 3 bytes until we reach here. The total of all of these is 1 megabyte. This is why we say byte, 1 megabyte, because all of this is 1 mega, which is 2 of power 20, 1 mega. Byte is what's inside this address or these addresses. So, for example, we have here 0f. 0f, or in decimal, we write it because 8-bit. We have 11110000. This is 0f. and see the other types of Intel microprocessors. This was for 8088. But before 88, there was 8086, and after 88, 8086, etc. And this table gives the details of the address bus size, the data width, and the memory size. So we now understood what's memory size. The memory size, we understand it from the address bus width. From address bus width, 1 megabyte, 1 megabyte, because the data that will be carried on this address bus of size 8. But this one, 8186, it has 20, but the data bus here is not 8. Here we should have 16 fields for 16 bits, which we called it word, a word for Intel family. And see, here we have larger data bus width, bigger. Here also, and here is the largest address bus. This is why we have here 64 gigabyte. Assembly language programming. An assembly language instruction consists of a mnemonic, or we call it opcode, optionally followed by one or two operands. What's an operand? The operands are the data items being manipulated, and the mnemonics are the commands to the CPU, to the microprocessor, telling it what to do with those items. This is an example of the mnemonic and operands. So what this instructions in assembly language says, it says copy the source operand, because this is the opcode. This is the mnemonic or opcode that will do some specific operation, operation code. So this code to do some operation, to do an operation, this code move. What operation is to do is to copy. Move, it means copy the source to destination. Take the contents of this source and copy it into this destination. This, all of this called operands, destination and source. In real assembly programming, we write this instruction. So the destination here is AL. What's AL? AL is a register. And this is the source. The source is a number. Here is a hexadecimal number. So what we want to do this instruction, to move, to copy actually, to copy this instruction into AL. This is register, AL. So after finishing or completing this instruction, after doing this instruction, AL will have this number, 25. The 8086 and 8088 microprocessors are functionally identical, except that 8088 has an 8-bit bus and the 8086 has a 16 data bus. The basic operation used are as follows. Fetch the next instruction the next instruction from memory, then read the operand if required by the instruction. An operand is a quantity to be operated on as directed by its associated instruction. And finally, execute the instruction. Do what the instruction says. This is the final step actually. Execution was before writing. Then finally, number 4, write the result back into memory if required by the instruction. The basic processing steps are performed in 8086 and 8088 by two separate internal units. The first unit is the execution unit. The execution unit decodes instructions fetched by the BIU. This is the second unit. BIU means this stands for Bus Interface Unit. So the EU decodes instructions fetched by BIU, generates appropriate control signals, and executes the instructions. The main parts of the EU are arithmetic logic unit. Arithmetic logic unit. Arithmetic or logic unit or ALU. This part it executes the logical and arithmetic operations. The main parts of the EU is the ALU, the general registers and the flags. So here we find here ALU and the registers, we find registers and flags. We call it general registers. Some registers, we call them general registers. We will see that in details. Bus interface unit. This unit interfaces with the system buses and fetches instructions, reads operands, and writes results, and interact with the EU and the system buses. So this is the major part of the BU are the segment registers. So the major parts of the BIU are the segment registers, the instruction queue, and the instruction pointer IP. Pipelining with the execution unit is executing one instruction, the BIU can be fetching another, ensuring that the queue will always be full and that no time will have to spend waiting for an instruction fetch. This technique is called pipelining. We have in the regular operation, we fetch the first instruction, then execute the first instruction, write the result of the first instruction, then fetch the second instruction, execute the second instruction, and then fetch the third, read operand, execute the third instruction. As we see here, we complete the operation of each instruction. We do not go to the second instruction until we complete the first instruction. And then After fetching the second instruction, we we wait until we finish from the second instruction, then we go to the third instruction. But this is the elapsed time for this kind of operation. But this is not the same case for pipelining. This is the serial fetch execute the non-pipelined operation. For pipelining, we first fetch the instruction, execute the first instruction, fetch the second instruction. See how when we fetch the second instruction in this time, at this time. But here in the serial type, we fetch it here. Execute the second instruction, write the result, fetch the third instruction, read operand, and execute the third instruction. So, see, at this time, we are done with two instructions. But in the first type, we are done with two instructions in this elapsed time. This is the EU and this is the BEU. So the EU, the execution unit, will do this task. The BIU will be involved in these tasks. So see here, fetching, writing, reading, and executing the instructions. But here, execution only, the instructions. Execution of just executing the instructions. This is the pipeline, or also called overlapped fetch execute.